Okay, everybody, so for today's video, we'll be talking about something called the epsilon-delta limit definition. Okay, so we've talked about limits, and I guess you could say in this video, I'll tell you what limits really are in their full precision, all right? And it can be intimidating when you look at the definition. It certainly looks complicated to most people, and it's got the Greek letters epsilon right here and delta in it, and for most people, it's probably bad enough when you start using letters to do math, but when you start using Greek letters, I think it gets even more intimidating. Now, I don't think the right way to do this is to just jump right in. All right, so we'll get back to this slide, and I just want to spur your thinking in the right direction before we talk about the epsilon delta limit definition. Okay, so just think about this. So say I have this function, y is equal to 2x plus 1. And say I tell you a limit that you can probably agree about. The limit as x approaches 2 of 2x plus 1 is 5. And so far what I've told you in previous videos is what this means, or a way you could think about this, is that if x is close to 2, that will make y be close to 5. All right? And we've done things such as make tables in order to illustrate that. I've made tables like this in other videos addressing this topic. And you can see that if the x gets closer and closer and closer to 2 from either direction, that will cause the y to be closer and closer and closer to 5. All right? So far that's what I've told you. But, close is, just to say that is not very precise. So we need a way to quantify or measure how we're using the word close in this statement, okay? All right, so that is our objective in this video, is to quantify and measure what we mean by close, okay? Because just to say close, that's not, mathematics is a lot more precise than that. So here's another question to think about then. Suppose we want y to be within 0.01 units of 5. Suppose that's our objective. How close does x need to be to 2? So there, when I ask you how close, you're going to give me a number, right? You're going to quantify it or measure what I was talking about up there. We already know if y is close to 5 is linked to x being close to 2, but say you want it to be this close to 5. How close does the x need to be to 2? So here's how I'll show you how to do this. It's definitely not the only way, but it will get the point across. So I will do this visually for people that like to think about things visually. So let's say here is what the line y is equal to 2x plus 1 looks like, roughly, okay? I don't really have any scale that I'm sticking to with this picture, but that's good enough. That will get the point across. And it is true that, not only if x is close to 2, that y will be close to 5, but as a matter of fact, if x is 2, then y will be exactly 5, okay? And what do we say we wanted to happen? We wanted to say that we want y to be within this tolerance of 5. So if you want to be within 0.01 units of 5, I guess that would put you as high up as, well, so what's this number? 5.01? Or maybe as far down as 4.99. Okay? So that's where we want the y. So you look at this interval right here, 4.99 up to 5.01, and we want y here. All right, what does the x have to be? In a function, the x goes in and the y comes back out. That's what functions are. So where do I need to put the x down here? It's got to be as high as 2 point something and as low as 1 point something. How do we figure out those numbers? Well, you see how all the x's and y's are linked together, right? Every x gives you a y in a function. So I need to figure out this number, which I'll call x2, in this number, which I'll call x1. x1 gives you 4.99 for y, and x2 gives you 5.01 for y. If I could tell you what those are, then I could tell you how close the x needs to be to 2, right? If I just knew those numbers, I'd have it. It's not that hard to solve for those numbers, though. Okay, it really isn't. It's like I'm trying to figure out what x gives me 5.01 for y. So it's like 2 times x2, where I'm talking about that number right there, plus 1. Okay, so I plug that in for x. I get y, but that's 5.01. And then I'll just solve it, right? I'll subtract the 1, and I'll divide by 2. I get 5.01 minus 1, and then I'll divide that by 2, and I'll get my number. And then that's at least one side of it. And that's going to be 2.005. Okay, so that number right there, 2.005. So on the right-hand side, if you wanted to ensure that your y was here, you'd have to plug in, nothing higher than 2.005 for x. Okay. This other number, what about x1? We can find that the same way. So 2 times this number x1. Whoops. 2 times x1, that number right there, plus 1, okay, that will give me y to be 4.99. See how that's linked together, so 4.99. All right, we'll solve for x1, and that will involve doing this and this, right? Okay, and then we get for that 1.995. So that number right there, 1.995. So that's where my x is going to have to be. Okay, we're going to need x here. If you want y to end up there, you're going to need x here. That means any x you choose somewhere from 1.995 to 2.005, that'll put you somewhere up here within 0.01 units of 5. Okay, and I think the picture explains that pretty well. But how close though? Okay, how close? Well, I need to choose x within 0.05 of 2, right? How far is this right-hand endpoint? From 2, 0.05. How far is this left-hand endpoint from 2? 0.05. 0.005, sorry. So 2 minus 1.995. Okay, so let's write our answer in those terms. Okay? So we'll say we need x within, I was going to give you an answer to how close, 0.005 units of 2. All right, there's my answer. There's my answer to how close the x needs to be to 2. Now, when we've done that, we've quantified what we've talked about informally earlier. Earlier, when we started learning about limits, and we just said, if x is close to this, y will be close to that. Well, now I've like attached measurements to it. All right. Okay. So we say we got that down. Let's look at this more complicated thing, and I think that it will only seem more complicated to you. But here it is. All right. So the epsilon-delta limit definition. So there's the Greek letter epsilon, and then here's the Greek letter delta. And what's the real meaning of, say, this statement? Okay, so say I give you this function, y is equal to 5x plus 3, and I say, like, okay, well, the limit as x goes to 3 of 5x plus 3 is 18. Okay, so say we can do that limit. Now, here's what that means. I'll read this to you. I'll explain a little bit about it. This means that for every epsilon greater than 0, so no matter how tiny that number is. There is a delta greater than 0 such that, and then we get these statements with inequalities. This one means that if x is delta close to 3, so if the x is within delta units of 3, that's what this means, then the y will be within epsilon units to 18. Now that's just like what I was telling you before. This might seem like a vague or ambiguous, complicated statement, but it's just like this. You know, no matter how close I wanted the y to be to 5, there would have been an answer to how close the x needed to be to 2. Like, I used 0.01, but no matter how tiny that number was, I could have gone through this and I could have told you how close the x needed to be to 2 to make that happen. It's really the same thing, all right? It just says that no matter how microscopic that number is, you know, there is a number, a tolerance for the x that'll put the y that close, okay? All right, so yeah, we want the y to be within some microscopic tolerance of 18. Well, there's a tolerance about the x that will cause that to happen. All right, so you can read the statement for what it is, but that's my commentary about it. All right, and you might see the questions asked like this. So say there's this statement, the epsilon-delta statement, and the question might go something like, well, suppose epsilon is 0.01, what is the delta? Now, this might appear to take a different form than what I was already showing you, but it's just like this. That's why I showed you this first. It's just like this. It's just like saying, I want the y to be within 0.01 units of 18, okay? How close does the x have to be to 3? All right? Now, we should know how to answer that, okay? So here's my interpretation. Okay, so I do this visually. You can solve it right out of the inequalities, but I think for most people at this level in calculus, that makes it look unnecessarily complicated. I think they'll understand it more if I do it this way. So I'll say, well, you got your xy plane. You got your function y is equal to 5x plus 3. And sure enough, if x is 3, then y will turn out to be 18. Okay, and it's also true that the limit as x goes to 3 is 18, all right? So yes, if I want you to be within some microscopic neighborhood of 18 for y, I can tell you how close you need to be to the 3 for the x, right? That's what the epsilon and delta are. The epsilon is the tolerance on the y value, and the delta is the tolerance on the x value. So our numbers look like this. So what was our y tolerance? Say epsilon 0.01. Okay, so 18.01. Okay, and then on the other side, because this just means within 0.01 units of 18, so 17.99. All right, and if we can find these x's down here that are linked up to those y's, well, then we'll have our delta, right? Our delta is the tolerance on the y. So, okay, I got to find this number x2, and I have to find this number x1. Okay? All right, so let's see. x2, you plug the x into that, and you get the y. x2 for x gives you 18.01 for y, so we'll say 5 times this number x2 that you see right there, plus 3 is equal to 18.01. And then to solve it, it's a little bit of algebra like the other example. 18.01 take away 3, then divided by 5. Okay? All right, so 18.01 take away 3, divided by 5, and we'll get 1.002 for that number right there. Oh, wait, no, that can't be right. All right, there it is. It's 3.002. Whoops, okay. So 3.002 here. On the other side, I'll just do, you could set it up and solve for x1 the same way. And you'll get for that number 2.998. Okay, so each of these is within 0.002 units of 3. So that's our delta. Okay, that's how close we need the x to be to 3. All right. Okay, so let's state our answer that way. 0.002. To ensure that y is within 0.01 units of 18, we will need to choose the x within 0.002 units of 3. Okay, so that's what our statement says. All right, so I'll show you another example. Before I leave this behind, I'll emphasize one more thing. That notice that it says if and then, as if any choice of x that close to 3 will cause y to be this close to 18. Yeah, so like any number in there that you could choose for x will put you up here within 0.01 units of 18. All right, so the epsilon and the delta are the x and y tolerances in the limit definition. And for the most part, once you see the picture, I think you understand it, and it takes a little bit of algebra to solve it from there. So let's do one more example. Let's do this one. So say I give you a limit. The limit as x goes to 0.25 of root x is 0.5. And you could make a table to establish that limit if you wanted to, but I mean, the square root of 1/4 is a half, and so it's reasonable to think that if you're anywhere near 1/4 for x, the y will also be near 1/2 for y. Okay? All right. So anyway, say I've got that like the others. All right. And then suppose I give you some kind of epsilon for it. Okay. So let's say epsilon is 0.1. All right. And by that epsilon there, I'm saying like in the limit definition I just gave you. All right. So if epsilon is 0.01, then delta is equal to what? All right, so I want to do this the same way as the others, which is visually. You can try to solve the inequalities if you want to, but I'm trying to appeal to the most people that I can, which means that I'll draw a graph where you can see everything, okay? So, all right, there is our graph of y is equal to root x. All right, okay, so our limit establishes this much. That if x is, in fact, 0.25, then y will be, in fact, 0.5. And if x is anywhere near 0.25, the y will be somewhere near 0.5. Say we want to be within a tenth. Okay? So when we say epsilon's 0.1, what are we saying? We're saying, well, we want the y to be as great as 0.6 and as small as 0.4. That is what we're saying, okay? Because that's my y tolerance. That's how close I want to ensure y is to 0.5 based on my choice of x, okay? So when I write this down like this, I'm just saying for that particular limit, that I'm understanding epsilon to be 0.1. All right, so that's the statement that I'm making. But I think by now you probably know what to expect. If I could figure out where these numbers are, then I would know what to tell you for delta. I would know what my tolerance is on the x. I'd know how close I need to be to 0.25. Okay, so this is x1 and this is x2, right? So let's figure out those numbers. So you put x2 in here, and you get 0.6 for y. Okay? So we'll say root x2 is equal to 0.6. And then we aim to solve that equation for x2. In this particular equation, we can solve by squaring both sides. And we'll get x2 is 0.36. Okay? So that number right there, 0.36. this other number, x1, we'll solve it in the same way. We'll say root x1. What would x1 give you if you put it into this function? It would give you y to be 0.4. So we'll say 0.4. And then we'll solve it the same way. We'll square both sides. And we'll get x1 is 0.16. Okay, so that number right there is 0.16. Now, what makes this one different from the others that I've showed you so far is that it's from our x value on our limit, it's a little bit further one way than the other, okay? So let me zoom into this and show you what I mean. So say you got like 0.25 right here, and then we've got like 0.36 here, and we got 0.16 there. Then there's where we want to be as far as our tolerance goes. And I just note that from here to there, that would be 0.11, right? Okay. And then from here to here, that would be 0.9, wouldn't it? Okay, okay. Which number is it? In the other examples I showed you, it was the same distance on either side. You know, from here to that boundary was 0.005 units, and from here to this one, it was the same distance. Now here they're different. So how would you think about which one we want? Okay. Well, all right. I know I could just tell you. It's not hard to just tell you, but I'd like you to think about it a little bit. I'm saying that there's this tolerance on the x, that if you choose the x that close to whatever the number in your limit is, then the y will be guaranteed to be epsilon close. So should we choose the bigger or the smaller number? Okay. Well, if we said delta was 0.11, well, going 0.11 this way would take you out of this interval. Bottom line is we need the x here. Okay, I need the x here. But what's a one number tolerance on 0.25? It'd have to be the smaller number. If you made it the bigger number and you said you need to be 0.11 units from 0.25, well, 0.11 units that way takes you outside of the interval that you'd need to be in. Okay, so we'll take the smaller number. All right, and delta will turn out to be 0.9. Okay. Oh, I put 0.9. I'm sorry. 0.09. Okay. So it'll be 0.09. You're probably thinking the whole time, why 0.9? Well, so 0.09. So delta is 0.09. There's our answer.